Okay. So this is chapter 10 is actually this chapter is also application of Bernoulli's equation in a real fluid. And you have seen in last lecture sheet 9, we solved some problem, 3 or 2 problem. There was frictional head loss, but it was given data. The frictional head loss equal to 5, equal to 6 meter or 5.2 meter. But so that's why you don't need to use the Darcy-Weisbach's equation. But right now, in this chapter, we'll figure out how you can find or calculate the frictional head loss in the pipe based on the Reynolds number and the viscosity of the fluid. So let's go through the slide. So Bernoulli, he derived the equation based on assumption. For simplification, he ignored the viscosity of the fluid. He say there is no viscosity of the fluid, and so what will happen? If there is no viscosity of the fluid, then there will be no frictional loss, and velocity of the fluid at the boundary is not 0. That means there will be slip between the fluid and between the surface of the, say, pipe. Okay, and velocity distribution is uniform because there is no viscosity of the fluid. So if you have viscosity of the fluid, then the velocity distribution of the fluid will be uniform. That means at the wall is this much, then middle will be the same. Everywhere velocity profile is same. Even at the wall is not 0. This is the velocity profile of a ideal fluid if you ignore the viscosity. But in reality, this velocity profile is come like that if you think fluid has a viscosity, because fluid particle right over here, the velocity is 0. Over here is 0, but at the middle velocity is the high. That is saying that velocity distribution is uniform over the boundary in case of ideal fluid. But in real fluid, fluid has viscosity, and due to viscous effect, the fluid particle has 0 velocity at the boundary. At the boundary mean at the surface of the wall, and there will be a frictional loss in the flow. And it's saying in case of real fluid particle from the wall will have the higher velocity. That's it saying. And there will be a change of velocity across the flow. That means change of velocity means velocity gradient, and there will be a viscous shear resistance, or there will be a viscous shear. Why? Because we know Newton law of viscosity, that tau equal to mu du by dy. What is du by dy? That means is the velocity gradient in the flow. For example, if you have a pipe this much diameter, and I like to see the velocity profile right over here, then velocity of the fluid particle at the wall will be 0. Then say right over 0, this fluid particle will move a little bit further than the wall. He will travel further than this one. Then this one will travel further than him. And at the middle, it will travel more faster. And similar, it will be symmetric velocity profile will be in the both sides. So if I think this is my x-axis, this is my y-axis, or you can think that this is the U along this direction. So this is the, sorry, 1 second, velocity U, and along this direction Y. So what do you see over here? That means velocity along Y direction is changing, right? Is changing, because along Y direction velocity is not the same. That is saying that change of velocity across the flow resulting in velocity gradient. That means change of velocity in respect to distance, and there will be a viscous shear resistance in the flow, or viscous shear stress. For example, you have a solid pipe, say made of stainless steel. You are carrying high speed fluid, say liquid petroleum, you can carry, right? And instead of pipe, steel pipe, you same pipe, you just same diameter, just make it the polythene. What will happen? You will see all the plastic pipe or polythene pipe will be wrinkled in the face, because at the wall there will be a force along this direction. That is called shear stress. Okay. So this is the property of the real fluid. Now, when you go for job interview, sometimes they ask some question, and that what is the duct, what is the pipe, and what is the tube. For example, if some mechanics come in your home to fix your air conditioning unit or refrigerator, they will say, I need some copper tube. They don't say I need copper pipe, right? But in same other mechanics like plumber, they came in home, he might say, okay, you need to buy some pipe. So what is the difference between pipe and tube? And other thing, we use duct. What is the duct? So you see the term pipe, duct, and conduit. Conduit mean is a channel which carry the fluid. It's called conduit, are usually interchangeably for the flow section. They mainly use for the flow section, and sometime instead of pipe, you might call is tube if diameter is very small. And the same type of flow, if flow diameter is very high, you can call it pipe. And when you call it duct, if you are use non-circular, then cross section, then it is called duct. Non-circular mean your cross section might be a square, might be rectangular, or even it might be a triangular. For example, if you visit some commercial building, you will see they use the rectangular duct for air conditioning unit. So what is the definition? So it's saying in general, flow section of circular cross section are referred to as pipe. If they are circular, then we call it pipe, especially when fluid is a liquid or might be gaseous. For example, all the natural gas flowing around the Dhaka city from Kumilla to Dhaka is flowing through a circular pipe, right? Flow section of non-circular cross section, if flow section is non-circular, then it is called duct. And in the duct, normally you will see it flowing low pressure air or gases. And smaller diameter pipe is referred to as tube. So you will see all the high pressure fluid or liquid or gases normally carried out by a circular pipeline. But if cross section is very small, then instead of pipe, we call it tube. And if cross section is not circular, then it is called duct and normally carry out air or gas. For example, in the air conditioning unit, what happened? In the duct, through the opening of the duct, bottom of the duct, there is some hole. Through the hole, air is coming out in the room from the rooftop or from the site, right? That is work in the air conditioning unit. So what is the problem? If you use the rectangular pipe to carry the high pressure gas, there will be two things. Number one thing, frictional loss will be high. If you use the rectangular cross section, there will be frictional loss. Velocity will be reduced. If velocity reduced, then what will be happen? Pressure will be high. So for example, this rectangular cross-section pipe, you are carrying high pressure fluid. Then what will be happen? Inside the pipe, there will be high pressure working upward, right? All the way in the bottom too. And this small section at the upper portion, if you think as a distributed beam with support at the both end, then what will be happen? You get support right over here, support right over here, right? And outside, what pressure you have? In the outside, you have atmospheric pressure, but atmospheric pressure is low, right? So in that case, this edge will deform like that. Similarly, this edge will be deformed. This edge will be deformed like that. So that's why if pressure difference between inside and outside is P atmospheric pressure, PATM, and inside PI. If this pressure difference, that means PI minus PATM, that is called delta P. Is this delta P is very high, then obviously you have to use circular cross section. It don't matter if carrying liquid or gas, because circular cross section deformation normally not that much. Even it has deformation, it will carry out deformation uniformly. Say outside, inside they have a pressure, so it will go a little bit bigger. But if you go bigger, it will go like that, all the way uniformly. But in rectangular, due to this corner, your deformation at the corner and end will be different. So it will be not a, after deformation, shape will be different, not a circle, not a rectangular. Okay. And normally rectangular cross section, that's why I don't use to carry the high pressure fluid. So you see over here, liquid, what is pipe and duct? Liquid are transport in circular pipe. This is because pipes with a circular cross section can withstand large pressure difference between the inside and outside without significant distortion, bikriti, deformation of the shape. Non-circular cross-section are usually used in applications such as heating and cooling system of the building, where pressure difference is very small. So in air conditioning unit, why they use the rectangular cross-section duct? Because the pressure inside is not that much high, just a little bit higher than atmospheric pressure. If it's equal to atmospheric pressure, then liquid will not come out through the opening at the bottom. So that's why this PI normally keep little bit higher than atmospheric pressure. So you turn on AC, due to the little bit higher pressure, it come out through the bottom. And other thing, any reason, if you close on portion AC vent, then velocity will be 0. Then pressure will be little bit increase. But this increase of pressure in the upstream will give you more air to flow down smoothly. But this pressure difference, obviously not that much. Say atmospheric pressure 14.7 psi, right? So right inside, you need to maintain like 16 or 16.5, around 17 psi. Okay. So a lot of time you go job interview, they might ask you what is the difference between duct, pipe, and tube. Why a rectangular cross section pipe is not used to transmit a high pressure fluid? What is the example? What is the reason? Or they might ask why rectangular duct is used in the air conditioning system instead of circular pipe. Now, what is the laminar flow and turbulent flow? We already discussed, right? Lot of time. Like in laminar flow, this is laminar flow. They put some color with a flow. You say this is the duct or pipe, there is a flow. So with a E-tube type device, they put some color. And when you put color, you say all the color, the flowing in a line. They're not flowing along this direction. That means flow is laminar. Similar way, you put some color over here in the right side, you see some portion of the fluid little bit going straight, smoothly, then fluctuating. Okay. Then they are fluctuating heavily within this region. That means from here to here, that means this region, from here to here, this region is called laminar flow. And this region is called transition, and this region is called turbulent flow. Okay. And here is I try to show you some example of laminar flow, transition, and the turbulence flow. You see right over here, this region, like this region is laminar. But this region, you see, steel flow is laminar, but is not like to stay in the laminar. From here to here, you see it's changing over here, changing over here. Then right over here is completely changed. So that means velocity is fluctuating. So this is laminar flow, this is transition, and this is turbulent flow. And most of cases, we use turbulent flow in the to transmission liquid or fluid gaseous media, because if you have flow is turbulent, that means higher velocity, your head loss, frictional head loss will be reduced. Okay. There is a other example of laminar, turbulent, and transition flow. This portion obviously is turbulent. From here to here is laminar. But you look this portion, some fluid going to the outside, this region, right? So this portion is called transition flow. Okay. Now, there is a one thing we need to know, that is called hydrodynamic entry length. What is that one, and why you need it? For example, you are working in a chemical industry, and there is a pipeline, say this much size. This pipeline is connected with a tank on the left side. So what happened? There might be some, say, bulb over here. You open the bulb, fluid will enter right over here, right? Now you need to install a benchrometer or orifice meter or a pressure gauge. Now where you will put it? You can put anywhere, right? You can put it right over here, right over here. You can put it right over here, right over here. Anywhere you can put. But what is the appropriate location? Should you put over here, or should you put just close to the wall? So that we need to check it. So there is a one thing is called completely full velocity development. What is the full velocity development? For example, a fluid passing through, say this is your balcony, 6 feet wide. Okay, long length is, if I draw 3D view along this way is length. Okay, this is your wall of your room. Okay, so in winter, it's a cold air is coming. So they'll pass through the bottom. They will go over here, right? In the bottom, they will not go in the bottom right way. Okay, what I'm saying, the fluid particle immediately close to the hitting at the tip, he will stop. Because why he'll stop? Because due to the viscosity, right? Oh, I messed up again. Okay. This is our wall balcony. So if I like to draw a fluid particle just hitting at right over here, what happened? His velocity will be stopped, right? So because due to the viscosity. So I am saying right over here, we have a long line, you just imagine a line. And we are thinking the fluid particle one is over here, right over here, right over here. Let's consider the bottom one. Say fluid particle on over here, other on over here. So after 2 seconds, this will not move because his velocity is reduced due to the shear stress or viscosity of the fluid. But this one, he will try to move toward the right, but this one will restrict him due to the viscosity, because he'll say, hey, don't flow, please stay with me. So this fluid particle, he will travel little bit further than him. So say he's coming right over here. But next one, this one will travel more than him, usually coming right over here. So gradually, say, if I think this is a fluid particle, he will travel a little bit higher, right? So if I connect all the line, then how I'm getting? I'm getting a line like that, right? Say all the air coming with velocity 10 or 100 mile per hour. So fluid particle, this one have velocity 0, right? He has a little bit more velocity. He has more than this velocity. At one stage, we'll see right over here, this fluid particle traveling with a speed of 99% of free stream velocity. That means heat velocity will be, if this velocity is u, his velocity will be 0.99 u. Then this portion is called boundary layer thickness. That means at a distance from the tip, we'll see fluid reaches at a velocity 99% of the free stream velocity. Similarly, you will have one more at the top. So this area of fluid, it will not move very slowly. Same thing right over here, very slowly. Okay, so that's why, especially if you visit village in the winter, you will see the tin shed house. If you have a balcony, you see water is dropping due to condensation, because due to the cold air, say velocity is very low. So cold air, if you have balcony, right over here coming cold air, he will stop, and at the wall there will be a boundary layer also at the bottom. So temperature of this portion is always cold. So you will feel more cold in winter in a tin shed house. Other thing, say if you visit or traveling in a boat or traveling in a launch, you will see if I look from the top, this is your front portion of your boat is heading along this direction. How water flow? You see some portion of water is going like that. And this portion is always remain with the boat surface because this portion has a low velocity. So this is going at the high speed, say 40 miles per hour. What will be velocity of this fluid particle? He stick with the wall of the boat. That means he will get same velocity of the wall. But all the fluid going along this direction, free velocity, so is flowing 10 miles per hour. So this fluid particle will move with the boat along this direction, right? But gradually move from the wall, this one, if this move with 30 miles per hour, this one velocity will be less, might be 38 miles per hour. This one will be more or less. And right over here, fluid velocity will be close to this free stream velocity, 10 miles per hour. So that's why always you see this kind of shape. So this right over here, this thickness is called boundary layer thickness. And you will learn more in the boundary layer thickness about the second part, okay? So just remember, if there is a flat plate, velocity profile will be like this one. Right over here, velocity profile will be 99% of free stream velocity. If right over here fluid coming with velocity u, then this thickness is called boundary layer thickness. Okay, that will be enough. So if we go back to the previous slide, you see, 1 second. We are considering the fluid entering a circular pipe with uniform velocity, right over here with uniform velocity. So velocity of the fluid particle at the wall right over here will be 0. Then you taking the cross section right over here. And how much he traveling? He traveling from this much distance, okay? We are taking only 2 fluid elements. If you considering right over here is right over here, but this fluid particle travel a little bit faster than the average velocity. Same thing, you take cross section over here. This fluid particle has velocity 0, but this one travel more than this distance and more than average velocity. So he's coming this much distance. Similarly, right over here, velocity is 0. And this one travel more than average distance and also more than previous position. Similarly, right over here, velocity 0, and he travel more than this distance. Now, if we consider the middle one, then the middle one, he travels same as average velocity. Right over here, you see, this is average velocity line right over here. He travel more than average velocity. And at the middle, he travel more, you see. And right over here is more, right over here is more. That means right this point, velocity developed is called full velocity developed because it reaches 99% of free stream velocity. Now, if you connect all the line of maximum velocity, then you will get this kind of life. Similarly, at the other side, you will get this one. So actually, this one, this shape will be what kind? Kind of cone inside a circular pipe. Okay. So it's saying because of non-slip condition, fluid particle in the layer in contact with the surface of the pipe come to complete stop. that means velocity 0. This layer also causes fluid particle in the adjacent layer to slow down, and gradually there is a result of friction. There will be friction between the layer of the fluid and developed a velocity gradient along the pipe. Velocity gradient means change of velocity with respect to distance. Now, what is our target? You say this distance, we need this much distance to develop the full velocity. So, if you install a equipment, right over here, velocity is not developed fully because velocity gradually changing, gradually increasing. So if you install something in this region, then your result will be inaccurate. Even you say you install a flow meter or install a pressure gauge right over here or a benzodimeter, your result will be not right. That's why you need to put something beyond this length. So from here, you have hydrodynamically fully developed region. So right over here, if you put something, some flow measuring device or pressure gauge or benzodimeter or orifisometer, you will be get accurate data. So we need to know the how you will calculate this length. Okay. So it's saying the length of the pipe or duct is required to achieve a maximum 99% of fully developed flow when the entering fluid velocity profile is uniform. So this length, right? This length velocity coming 99% of free stream velocity. So this is called velocity boundary layer in the bottom and at the entrance. So this length, after that, you see, you will not find that much velocity boundary layer because all the fluid right over here will be close to the wall, still will be 0, but they will still travel almost close to the free stream velocity. So this length is called hydrodynamic length. Now, how will figure out? If flow is laminar, then hydrodynamic length will be this much, 0.05 Reynolds number into D. If length flow is turbulent, then it will be equal to 10D or 1.35 D into Reynolds number to the power 0.25. Okay. So by calculating this length, you can figure out that how far I have to install the certain gauge or certain meter. Okay. Now, we need to know the one more equation is called impulse momentum equation. So what is impulse momentum equation? It's saying impulse momentum principle, we state that impulse applied to a body is equal to the resulting change of momentum. So what is impulse and what is the momentum? We can figure out from Newton's second law. Newton's second law that F equal to ma. And F equal to ma, a acceleration, that means change of velocity divided by the time. Now change of velocity, we can write down v2 minus v1. So finally we get this one, right? Now this is equal to F. Now, what is impact actually? Say a cricket ball coming with high speed from the bowler, and you are the batsman. You hitting the ball with certain energy, force, for how many seconds, how many minutes, very fraction of time. So you applying a high force very short amount of time. So force into delta T, that is called impact. So impulse momentum equation, it say that impulse on a body is equal to the change of momentum. That means F into T equal to change of momentum mean Vorbeck. So you will get delta mv. Now delta mv for solid body, m remain constant. So for solid body, you will get v2 minus v1, right? And this one also you can figure out by Newton's second law. So just remember what is the impulse over here, and remember impulse force or impulse equal to change of momentum. So right over here, this is I. I is the impulse. Impulse equal to change of momentum. Now from here, I can figure out F. So F equal to, if I put delta T, just the bottom of velocity, then hardly you get acceleration. But I like to, for solid body, you can put below Vt, delta T, because for solid body, your mass remain constant, right? For example, you're driving a bike and 60 miles per hour and hitting a tree. So your mass flow is not changing, right? Remain constant. But what is changing? Your acceleration. That means from the 60 mile per hour, suddenly you get stopped due to the hitting the tree within might be millisecond. That means you are driving certain force, your force equal to ma, change of acceleration. That force into some time, that is fraction of very short time, is called impact, that equal to I. And that impact is equal to change of momentum. Now this delta T, instead of putting under V, we put under mt. What does mean mt? That means m by T, that means mass flow rate. How much mass flowing per unit time. So we are getting F equal to m dot into V2 minus V1. Now, what is the m dot? The rate of change of mass. So we know m dot equal to mass flow rate equal to rho a v, or you can say a v equal to q. You can say rho q. So just this value of m dot, you put it over here. So we get F equal to rho 2 q2 v2 minus rho 1 q1 v1. So what is the application of this equation? Say you are working in a chemical company for a Middle Eastern company. They're making pipeline from Iran to, say, Afghanistan or Pakistan. And this is a pipeline. So you see right over here, or if you apply between these 2 points, what happened? Fluid is coming along this line, then changing the direction, right? So due to the change in direction, the fluid will put some force on the pipe. That you need to know. Otherwise, you cannot make the support of the pipe. Even sometime you might need to change the direction of the pipe just like a 90-degree angle. The fluid coming this direction, right? Then following in the 180-degree direction. So there is a high change of momentum. Even you have velocity same, say velocity v, 10 mile per hour. Along this direction also 10 mile per hour. So what is your change of velocity over here? Still is, if this one is v1, this is v2, then v2 minus v1, because this is vector summation. So ultimately what are you getting? v2 plus v1 into mass flow rate. That mass force will fluid will put on the pipe and pipe support. So that's why you need to figure out the amount of force due to change of velocity or due to change of momentum of the fluid. So how you can apply this equation between 2 points? If you like to use between these 2 points, say this is point 1 and this is point 2. So your F will be rho 2 Q2 V2 minus rho 1 Q1 V1. Say, right over here, flow rate, Q at this point. If you Q know, then you can figure out the velocity V1. How? V1 equal to Q by A. You can easily figure out. Similarly, you can figure out V2 over here because V2 equal to Q by A2. So you got V1, V2. If density is same, then what will happen? Rho 1 equal to rho 2. Then you need to say, what about the Q1 and Q2? Is same Q coming or some making branch over getting out over here, some amount of fluid. So if over here is Q1 and over here is Q2, then you need to figure out just value of Q1 and Q2. So overall, this is the equation to figure out the force in the pipe. So for liquid, normally is incompressible, right? So rho and rho 2 normally remain constant, okay? And if pipe diameter is same, then Q1, Q2 will be same. And when these two will be same, if these two will be same, then there will be no force on the pipe, okay? Any question so far? Any question? Anyone? Hello?
No, sir.
No? Okay. So let's we solve a little problem. Right over here, you see is showing a pump at pump P. Right over here, pump P. He's taking liquid or say water from a reservoir, and this reservoir maintain level of water from the pipe entrance always 1.5, and height of the pump from the reservoir you see 2 meter, and pipe diameter over here is given 150 meter. But at the outlet, instead of pipe, they are using a nozzle, say 7 diameter, 75 millimeter. So this is the figure. Now you need to say what they want. They are saying water is flowing, so liquid is water from a reservoir by a pump, who is developed 8 kilowatt on the flow. That means pump adding energy to the fluid is 8 kilowatt. This is the power of the pump. Find thrust on the pump support structure. That means how much force fluid will apply on the pipe or on the pipe support. If your support is very weak, then what will happen? Pipe will vibrate. Ultimately, pump will vibrate, support will get lost, then ultimately it will break down. So you need to make sure that your support is strong. This is the simple problem, but same thing might be your this height of the water. Pump. Instead of 2 meter, it might be 20 meter, or it might be 100 meter, or your pump might be right over here, and you are delivering in a water in a rooftop, say 7-story or 8-story building or 20-story building. Then how will figure out the pump support, or how will figure out the capacity of the pump? So that will be the application of this problem. So let's see how we can solve it. At least you need to know that what they like to know. They know thrust. Thrust mean forward push. That will be force. They like to know force. Then immediately you need to think in your mind that in the fluid mechanics, they have only one equation, that F equal to rho Q V2 minus V1. So rho Q, what is the rho Q? That m dot, mass flowing per unit time. So you need to immediately know that I have to use this equation, V2 minus V1. Then you need to remember that how you can get the each parameter, like first parameter rho, you already know, 1000 kg per meter cube. Now, how will you figure out the Q? Q is not given, even velocity is not given. But if you know the velocity, you can figure out the Q, that Q equal to A into P. So similarly, if you know velocity at point 3, you can figure out the Q. Yeah, area is given. That Q, you can put it over here, right? Then you need to apply a little bit cleverly. If you use the Bernoulli's equation between 2 points, like this point and point 3, then what will get? What data? You carefully you have to look. You will get what will be the V1? V1 will be 0 because you are maintaining constant height at the surface. Then what will be P1? Atmospheric pressure. If you think that this is your reference line, what will be your Z1? 0. And for 3.3, you will get P3, how much? Is releasing water to the atmosphere, atmospheric pressure. What will be Z3? Z3 will be this much height, right? And this will be B3, right? But B3 is unknown. If you know B3, you can figure out the Q, but you have two things you have. Number one thing, you can apply Bernoulli's equation between point 1 and 2. You'll get one equation, right? Other thing, pump capacity is given in terms of power, 0.8. So what is the pump equation? That power of the pump or turbine equal to rho G Q into H. So this power is given 8. This is head of the pump H and the Bernoulli's equation. These two equations you can solve. You can get the V3 or V1. V1 is 0. Obviously, you'll get V3. You got V3, then directly you can figure out the Q, then figure out the force. So let's see how we can solve it. Okay. Just solve this problem, then we'll keep it off. Okay, let's see. Stop sharing. Let me see. Okay, I open that equation. Just 1 second. Mathcut file seems like is not, I didn't open yet. Just 1 second problem. Okay, did you see, or sorry, I got to other one. Right over here. Did you see Mathcat file? Hello?
Yes, sir.
Yes, sir.
Okay. Okay, we'll go quick. You see, this is the figure. We already explained it. Now, this is the density of the water. Power of the pump, 8 kilowatt. D3, diameter of the nozzle, 0.075, given in millimeter, convert in meter. V1, 0. Z1, 0, because this is the reference line right over here. P1, P atmospheric pressure. V3, we need to figure out. And Z3, 2 meter is given already. P3 equal to P atmospheric pressure. Now, you apply the Bernoulli's equation between 0.1 and 0.3. So how we can apply Bernoulli's equation? At point 1, you have P1 divided by gamma, right? So P1 by gamma plus V1 square by 2G plus Z1. This much energy fluid have at point 1. Then you see coming down, pressure energy increasing, again going up by same amount. That means pressure energy no gain. Or right over here and right over here is the same point, right? Then fluid going with this energy coming right over here, he absorbing energy from the pump, or pump giving some energy to the fluid. So total energy will be right over here is pump. Then he is heading toward the point 3. Toward the heading point 3, how much energy will have? So if I use the equal sign, so on the way, what happened from here to here, he will lose some energy. A is LF. Then remaining energy will be get out through point 3. So P3 divided by gamma, right? Gamma plus V dot 3 square dot 3 square divided by 2G plus Z3. This will be your equation. So let's see that we write down right over here. Now ACLF. How will get the ACLF? ACLF, you need friction factor, or the formula ACLF equal to 1 by 2 FL. That means F times L divided by GD. FL by GD, I think it has a V square something. FL V square, okay. Right at the top, there is a V square, at the bottom to GD, okay. So what you need, you see, you need friction factor, you need length of the pipe. But you see between on this height given, but this length of the pipe is not given. So that's why we ignore the ACLF. So I am saying that ACLF head loss equal to 0. Now your V1 0, Z1 0. So P atmospheric pressure remain in the left side, right side P atmospheric pressure, B3, Z3. Z3 value is given 2 meter. And this term and this term will be out. So A spam equal to only this equation. Okay. Now, and other thing, you know that power of the pump equal to rho G Q H. So P pump equal to rho G Q H right over here. So Q equal to A into V3. Now, so Q, what is the V3? Pi by 4 D square into V3. D3 is already given. So right over here, you put 8 kilowatt of power. That means 8,000 Newton meter per second. You put rho. You put G, then Q. Pi by 4 D square into V3. Pi by 4 D square into V3 into H pump that I put over here, H pump. So after simplify, you get this equation. Now we have two equations. See, H pump equal to this one and H pump equal to this one. So I can say that both equation is equal. So from equation 1 and 2, you can write this one. Now, This equation, if you multiply by B3 both side, then coming like that. Now how we can solve it? Figure out the B3. This is part of your numerical analysis. You can use scientific calculator or you can use a MATLAB, something you can figure out. But you don't have nothing. How will you figure out? Just you apply your knowledge from numerical analysis by trial and error. So I can say right over here that you use just your calculator, but I'm not saying you need to know that through 2 years you learn the mathematics. What is the application of it? So right over here is application. I don't know what is the real value of B3. So just I am assuming that my value is 20 meter per second. So left side value, it will not change. I make 2 columns, right side, left side, and the difference. So you put 20 meter per second right over here, you get this value. Left side, you get this value. What is the difference? Still high. That means your value is very high value. You need to reduce the value. So I reduce the 10. I reduce the 10, then right side coming this much, left side coming this one. That means I need to increase more than 10. So this difference is negative. So instead of 10, I am now taking 15. Then right side remain this much, left side is constant, difference is this much. It's come down a little bit. Still, my value is little bit higher than real value. Okay, so I come down from 15 to 14. I make 14. Left side, right side, I get this one, left side, this one. So what is the difference? I less by 349. Still is little bit high. So this is negative. That means I have to increase than 14. Increase than 14, you can go back to 15. It will give you same result. So you just start with 14.5 or 14.6. So I start with 14.5. Left side is this much, right side, and left side this much. Difference is 4.24. So I think this is acceptable. You can put 4.6 or 4.65. You can try on more. So finally, I assume B3 equal to 14.5. This is the application of numerical analysis. Now, what I need to figure out? I need to figure out the force. So what is my force formula? This one. This is the formula. Rho Q B3 minus B1. B1 0. B3 14.5. What is the Q? A3 into B3. So you figure out the Q pi by, this is the area A3 into D square into V. Area into V, you get the Q. So this is my Q. Then you put everything over here, you get the force. Okay. So any question? Any question about this problem? Anyone? Hello?
Yes, sir.
No question?
No, sir. No, sir.
Okay. So we can leave it here, and remember Thursday, that means tomorrow we have a class at 11:20. Okay.
Okay, sir.
Okay. Thank you very much. Have a good day.